Farnborough, the site of the world-famous air show. But for much longer, Farnborough has been the home of the Royal Aircraft Establishment, a unique organisation with a remarkable history. Today, the Royal Aircraft Establishment is acknowledged as one of the world's foremost aerospace research centres.
Right, beginning to close up, closing up now.
The RAE is the air systems establishment of the Ministry of Defence. Its roles include assessing potential military threats to the UK and spearheading the advances in technology needed for future aircraft and weapons. Many of Britain's leading aerospace engineers and scientists work here and at other RAE sites across the country. The establishment also undertakes civil aerospace research on behalf of the Department of Trade and Industry and for the British aerospace industries. As with any successful organisation, its strength lies in the dedication and skills of its people.
And a Reynolds number of 4 million per foot. Pitching.
Well,
The expertise of the RAE's scientific and engineering staff covers a wide range of technological disciplines. The RAE has facilities at several locations across the country. At Bedford, there is a range of wind tunnels, including those for testing aircraft designs and guided missiles at supersonic speeds. There is also a fully operational airfield for all types of flight test work. Engines for civil and military aircraft are tested at Pystock, adjoining the Farnborough site. On the west coast are the guided weapons ranges, the main one being at Aberporth in Dyfed. At Farnborough and Bedford, a wide range of flight simulators are used to carry out research into aircraft control systems and cockpit environments. The RAE has been associated with most of the important advances in aviation. Research in the 1950s helped towards the development of the first successful vertical takeoff and landing aeroplane, eventually to become the Harrier. A great deal of research work for Concorde was carried out by the RAE. The major structural fatigue testing was done at Farnborough, engine research and development work at Pystock, and the aerodynamics were refined in the wind tunnels at Bedford. The scope of RAE capabilities covers the whole field of aerospace technology. Research work is underway on a new generation of combat aircraft for the year 2000 and beyond.
Okay, Terry, I think we can take data.
As in the past, the RAE's role will be to work in partnership with industry to take this next important step in aerospace technology.
Plus 10 degrees coming up.
At Farnborough, Pystock, Bedford and other sites across the country, teams of RAE researchers and technicians are working towards this goal.
1707.
The whole approach to modern combat fighters is changing. In the past, the aim has been to design stable aircraft. But new technologies allow aerodynamically stable aircraft to be flown, offering major performance improvements. The new unstable designs mean that aircraft can be smaller, cheaper, and yet have a better performance.
Or a canard to trim with. This has both, which should offer greater maneuverability in a flight regime.
Combat aircraft also have to be highly maneuverable.
Motorized and can be...
The key to good maneuverability at combat speeds is the canard. This small extra wing controls and enhances the airflow over the main wing during extreme maneuvers. Together with the airborne computer, the canard has led to a breakthrough in combat aircraft design. Using a Cray, one of the new generation of supercomputers, it is now possible to calculate the flow field around a complex aircraft shape and to predict the performance on paper before committing a design to the hardware stage. This enables many more designs to be evaluated before one is selected for development. At Farnborough, they're running programs which are capable of visualizing the behavior of particles of air as they flow around the surface of the aircraft. These fluid dynamic calculations are only possible with the power of modern number crunching computers. As the mathematical model of an aircraft shape emerges, it is analyzed, modified and tested again and again until the characteristics are right. Only then is the idea put into practice in the shape of a model in a wind tunnel. This allows a comparison to be made between the computer calculations and the model's actual performance in the tunnel. If the computer results are confirmed, further improvements can be attempted, again on the computer, without the need for further expensive wind tunnel tests. These are the techniques RAE scientists are using as they probe the limitations of each new concept. Increased aerodynamic performance goes hand in hand with jet engine technology. The RAE possesses extensive engine test facilities. These were crucial to the development of the engines which power the Concorde, the Harrier, the Tornado, and many civil aircraft, including large wide-body types. Some of the test beds, like this one being used to develop digital control on a Tornado engine, operate at sea-level conditions. Others can simulate true flight conditions at high altitudes. The compressor and turbine are the heart of an engine. Research is aimed at improving aerodynamic performance and reducing weight and cost. Large, high-speed rigs are used to test new blade designs and to validate the complex computer programs being developed. Lasers are used to measure the airflow within the rows of rotating blades. In a modern gas turbine, the combustion chambers are required to raise air temperatures by 1,000 degrees centigrade or more in as small a space as possible.
Okay, ready for the next one? Yes, okay. Good light.
This is the field of reaction kinetics, the analysis of heat and mass transfer processes within the flame. Inevitably, the quest for improved performance has led to the development of new materials for airframes and engines. It has been known for a long time that the addition of lithium to aluminium would result in a lighter and stiffer alloy. But there were major metallurgical problems. A new alloy, known as 8090, which overcomes these difficulties, has been developed by the RAE at Farnborough. It's being produced by Alcan for use by the aircraft industry in the UK and overseas. The new alloy is being evaluated in the EAP aircraft and in the United States in the F-15 short takeoff and landing demonstrator, and will be used on future military and civil aircraft. Carbon fiber was invented by RAE scientists. Its use to reinforce plastic resins was first demonstrated at Farnborough. The new material is more rigid than steel, but only a quarter of its weight.
Personally, I think it's due to the fiber direction being at plus 45 degrees, while these sloping parts of the buckle are effectively at 90 degrees.
Because it's a moulded material, one can change the orientation of the fibres and the shape of the section along the span of the blade.
The advent of fiber-reinforced composite technology has made it economically possible to produce helicopter rotor blades in complex shapes.
How about impact damage and field repair, that sort of problem?
I think they should be proof against many of the problems we had with metal blades. Things like corrosion, scratching, accidental damage in service are not a problem with these blades. They have far superior fatigue properties, and we're very optimistic about the future for them.
The RAE and Westland helicopters worked closely together on the British experimental rotor program to produce a radically new blade design. Wind tunnel tests confirmed the great increase in lift predicted by theory. Westlands fitted the improved blades to a Lynx and recaptured the world helicopter speed record in 1986. The new EH-101, now on order for the Navy and the RAF, makes its maiden flight using the new rotor technology. Carbon fiber is employed extensively in the wing and tailplane of the latest version of the Harrier, which is in service with the RAF and the US Marine Corps. The Royal Aircraft Establishment and NASA are working closely together to move on to the next generation of this type of aircraft. Although it has had a remarkable success, the Harrier has limitations, both in size and its lack of supersonic capability. The UK and USA have agreed to pursue a collaborative research program to explore the prospects for a supersonic version. Once again, the scientists at Farnborough are being asked to look into the future and get it right. These design concepts are candidates for further development. Work being done at RAE will be important in the final choice. Engine configuration has a significant impact on the aircraft's aerodynamics. Each of these options is an attempt to address the fundamental problem of combining efficient lift with an advanced supersonic airframe. As technology advances, conventional methods of aircraft control are no longer adequate. The pilot's job is simply becoming too complicated without the aid of a computer. The RAE's large motion simulator at Bedford. This simulator allows a pilot to fly hypothetical versions of an aircraft across an artificial terrain long before the aircraft is available for flight testing. A computer program contains the aerodynamic characteristics. The aim of the simulator is to enable the RAE researchers to develop the computer-assisted control system for an aircraft. The combat fighter of the future will use a fly-by-wire control system, in which a computer is used to interpret the pilot's instructions to the aircraft. This fly-by-wire technology is now being extended to investigate control problems on future vertical lift aircraft.
Switch on the nozzle, I'll switch on the starter.
At RAE Bedford, the control system of this twin-cockpit experimental Harrier has been totally modified.
Fine. And again.
In the front cockpit, there are conventional controls as a safety backup. But the rear pilot has both types. He can switch from conventional control to computer at the touch of a button.
Could you put the charge on, please?
Yeah.
The combat pilot has to cope with enormous stresses from vibration, noise, and high G-forces.
About 30 seconds, are you ready?
Hang on a sec, let me check.
Okay, I'm ready.
Vibration is one hazard that the pilot can never be completely protected from. Depending on the frequency, he may even have trouble turning a switch. Other frequencies can actually prevent the pilot from sending a clear verbal message.
525. 005.
At the same time, he has to assimilate increasing amounts of information. Research is underway to understand and minimize these problems. Research into cockpit instrumentation and the development of combat techniques are carried out in a simulator which presents an artificial landscape over which the pilot can fly his imaginary aircraft.
Okay, turning on to heading.
In this case, the mission is a low-level attack on a group of enemy tanks.
Steering marker moving to the centre.
Low-level ground attack is one of the most difficult roles for the modern aircraft. The approach to the target is as low as possible to avoid radar detection and exposure to enemy fire. A miniature landscape terrain is traversed by a video camera attached to a periscope. When the video signal is presented optically through the windscreen, the pilot gets a remarkably realistic impression of low-level flight. The simulator copies exactly the pilot's commands at the controls.
Targets are there.
The RAF has long had the capability to attack targets at low level by day. One of the most important developments in the fast jet cockpit has been the use of infrared sensors to fly at low level and find targets at night. This has given the Air Force a major step forward in fast jet capability. These scenes were recorded on a dark winter's night on an RAE test aircraft flying low over mountains and valleys. Usually, these systems only look straight ahead, but now, work at RAE has resulted in a night vision system for helicopters with a much wider viewing capability. A tracking device above the pilot's head ensures that the thermal image camera points in the direction in which he wants to look, an important plus for a night-flying helicopter. Infrared techniques are particularly effective against vehicles such as tanks, which are readily detected by their radiant heat. This work shows how RAE research is helping the services to operate their aircraft as effectively at night as in daytime. Multi-role aircraft designed to attack a range of land, sea and air targets must be able to carry a variety of weapons externally without undue penalties in performance and endurance. Wind tunnel analysis will reveal any unusual interference in the airflow around the aircraft. The aerodynamic effect of objects such as fuel tanks or missiles needs to be thoroughly investigated if incidents like these are to be avoided. A tornado releases a cluster of bomblets specially designed to cause severe damage to the concrete surface of an enemy runway. Such bomblets are unguided. But newer technology employing miniature seekers is now leading to a generation of smart bomblets, which are able to seek out targets such as tanks.
Do you think you can sketch out a few wing designs and try those out?
Yeah,
for me?
certainly.
Okay.
At Farnborough, the technique of target identification using infrared imaging and artificial intelligence programs is progressing rapidly. This infrared image, recorded from a practice low-level attack, shows tanks, armored personnel carriers, and some civilian traffic. It is becoming increasingly possible for the seeker on the missile head to not only identify the target, but also the most vulnerable point to attack. In air battles, aircraft need to retain high performance even though carrying missiles, and the missiles themselves must be compact, agile, and precision-guided. This highly complex computer model of an air battle is helping RAE scientists to discover the right balance of characteristics needed for future combat aircraft. There is a major thrust in weapons technology today towards increasingly precise missile guidance. Rigs like this are used to assess the tracking accuracy of seeker systems while undergoing the extreme maneuvers made by guided weapons. With increasing precision, it's likely that explosive missile warheads may become unnecessary. This is known as the hit-isle concept. RAE's weapon technology and trials expertise allow it to help industry develop weapons with very advanced control systems, such as sea skimmers for attacking ships, and the Navy's vertically launched Seawolf. Seawolf, here being test-fired at RAE's Aberporth range, was developed by British Aerospace for short-range ship defence. With increasingly sophisticated and longer-range air defence systems on enemy ships, attacking aircraft must stand off at long range and trust the missile with the task of penetrating the ship's defenses. Sea Eagle, an anti-ship missile. Its onboard computer enables it to discriminate between real targets and decoys, and to hit the target where it will have maximum effect. Advances in technology will equip this type of missile with even greater intelligence to get it right in the endless battle of countermeasures. As the nation's centre for aerospace research, the RAE's work contributes towards civil aircraft design as well as to military aviation. The establishment's expertise and facilities are regularly called for in the multinational programme on the European Airbus series of civil aircraft. The high degree of accuracy which the 5-metre tunnel at Farnborough can provide is essential in establishing the performance guarantees which airlines demand from the manufacturers. Precise measurements will allow the payload and range to be determined well before the aircraft flies. Further improvements will be made to later versions. Equally important are measurements of engine performance and fuel consumption under realistic conditions in the altitude test cells at Pystock. Reducing the noise of the jet engines of civil aircraft has become increasingly important. In a jet engine, part of the energy released is converted into velocity energy in the jet which emerges at high speed through the exhaust nozzle. The trouble is that it makes a lot of noise. It's caused by the hot, high-speed gases as they emerge and mix with the outside air. In the huge anechoic chamber at Pystock, the RAE is helping British industry with this problem. It has been known for many years that bypass engines are quieter because of their much lower exhaust velocities and because they surround the main core of hot, high-speed air with a sleeve of cooler air coming from the bypass duct.
I'm ready to set conditions. Can I have MV air, please?
At Pystock, the RAE scientists are going a stage further and investigating what happens when some of the cooler bypass air is mixed with hot gases from the main engine duct. This work is aimed at maintaining the British lead in quiet civil engines. Space is becoming increasingly important for military and civil uses. The RAE is committed to research on the technology of satellites, their total systems and their operation. The National Remote Sensing Centre, the main UK satellite imaging centre, is part of RAE Farnborough. It provides satellite imagery from its computer-stored library and also carries out research into image processing and analysis. Farnborough, 1908. The first powered flight of an aircraft in Britain was made by Samuel Cody at His Majesty's Balloon Factory at Farnborough. The origins of the present Royal Aircraft establishment are rooted in the early history of military aviation. For many years, the establishment has been internationally recognized as one of the world's foremost authorities in both civil and military aerospace research. It is characteristic that aerospace requires extensive and large-scale testing facilities to support the innovative work of its scientists and engineers. Many of these resources, such as wind tunnels and computers, are state-of-the-art, providing the very latest technology for practical and theoretical research. The research groups of the RAE contain some of the leading authorities in a wide range of disciplines that are fundamental to aerospace work. Today, the establishment's role is to continue to provide research and development for its customers in the armed services and its partners in industry. Since the early days, one of the RAE's most important roles has been to look ahead and to establish research targets and objectives 10 or 20 years in advance. Not an easy role today, in the rapidly advancing field of aerospace technology, but a role in which the RAE has an impressive record for getting it right.